Hi, welcome back. So in this quick example, we're just going to continue to build on our 500 series, if you will, or the 5 series examples where we were looking at stresses in beams. And we're going to build on that and consider what would it do or how would it change if we introduced an axial load in conjunction with the beam and flexure. And so we're taking our example that we used in those series, and you recall if you go back to example 5.4, if you missed it, I'll put a card up here where we figured out what the stress distribution of this T-beam would be for the shown loading. Now, the only thing that we've done differently, though, is we've added a 5,000 kilonewton axial force to this and introduced the extra reaction that it would cause at the pin end on the left-hand side. So I've gone ahead and I've taken what we determined in 5.4, which was the normal stress distribution resulting from this, which gave us 80 megapascals in compression at the top as the maximum compressive stress, and 160 megapascals is the maximum tensile stress occurring at the bottom. And obviously, it varies linearly between the two, passing through zero at the neutral axis. And that's shown here in this diagram. So I'm not going to go back over that. Again, you can follow that card that I threw up there if you need to go back and remember that. But what I want to do is to look now at the stresses that would be caused in isolation by the 5,000 kilonewton axial force and superimpose the two of them together to see how that's going to change the normal stresses in the beam. I can think of lots of examples in real life where that might happen in a pre-stressed concrete beam or something like that, but we'll look at that more as we go along. So I'm just going to turn on my grid here so I can keep my pen marks all lined up. And so let's figure out what the normal stresses due to the axial load would be. So I'm just going to label that here. And of course, we know it's a normal stress. Label it as axial so we don't confuse it with the normal stress due to flexure. And you recall that is our load divided by the area. So in this case, we have our load, which we said was 5,000 kilonewtons, or 5,000 times 10 to the 3 newtons. And we're going to divide that through by the area. And we've gone ahead with the areas given in the problem as 30 times 10 to the 3 millimeters squared. So we run those through our calculator and we get 167 megapascals. And it's a tensile force, so that's going to be a tensile stress. So what I want to do is I'm going to draw the stress distribution from the axial stress. I'm going to get my ruler here. I'm just going to find it. And so I've already set up to do that. We see here, down here, I've got it labeled sigma equals P over A, and that's going to be uniform over the entire cross section in tension. So let's match what we have tension in the flexure diagram, and we're just going to put it in here and connect it up. And that's pretty much what you would expect from an axial force being applied. You have uniform stress across the cross section. And so from superposition, because we're limiting ourselves to linear elasticity, to get the result of the two of them together, all we have to do is simply add them together. So let's label this. That was 167 MPa there. And so if I add my key points together, I can add it together at the top and add it together at the bottom. We see that we're going to get a value here at the top, the 167 megapascals in tension minus the 80 megapascals, because it's in compression on the other side, leaves us with an 87 tensile stress of 87 megapascals, and we get 327 down here, 327, which is the 167 plus the 160, and that's tensile as well. And so we can go ahead and connect those two. And fill it in. And so whereas when it was solely in flexure, it was a combined compressive and tensile stress distribution. Now the entire cross-section is in tension because the axial stress distribution is dominating, although it's no longer uniform, of course. It has a variation top to bottom because of the normal stresses due to flexure. And so to answer the question then, it said, would it yield? So let's check for yield. And to do that, what we want to do is to look at where it's a maximum, and it is a maximum at the bottom of 327 megapascals. So we say 327 megapascals is less than the 350 megapascal capacity indicated in the problem, therefore no yield. And so now we're starting to see the importance of superposition when it comes to taking different components of loading and looking at them individually, applying the theorems that we've learned about each of those individually, and then being able to combine them later after the fact and getting the mathematical sum of them to know what the condition is within our cross-section or at a point where we need to check for maximum stress and everything else. So again, this was just problem 2 in a series of ever more complicated problems in combined loads. So I will leave a link here to the next video in the series, but also a link to the playlist as well if you just want to follow along with all of them. So hopefully that was useful to you, and we'll see you at the next video.